Okay, good afternoon, you guys. Yesterday we were looking at the quotient rule. You need to know the quotient rule, obviously, to find derivatives of quotients. The derivative of a quotient is found by taking the derivative of the numerator, multiplying that by the denominator, and then subtracting the numerator multiplied by the derivative of the denominator, and then dividing that whole shebang by whatever the square of the denominator is. The product rule, of course, is the derivative of the first times the second, plus first times derivative of the second. Quotient rule is a little bit more complicated. Your unit exam is scheduled for next Friday. We'll actually get, looks like maybe 3 days of review in there, so we'll get lots of opportunities for lots of practice. Does anybody have any questions you would like me to go over?
1e.
E? So we have root x over x squared plus 1. So before I go on, Enrico, just to check, is that the question you're talking about?
Yeah.
Okay. So I have to use the quotient rule here. There's no way that I could even rewrite that in some fashion so I could avoid the quotient rule. There's a way where I could bring that entire bottom to the top and write it as a -1 for an exponent, but you don't know how to differentiate that. We're going to learn that today. By the way, as a general rule, that reminds me, some of you after today are going to be tempted sometimes to take an expression like this and move the entire bottom to the top so that you can use the product rule, and I will tell you that that's a bad move. Okay? Using the product rule with negative exponents may seem like it's going to be quicker, but it's not. So if it's a quotient, stick with the quotient. There's an exception to that. When that exception comes up, I'll tell you about it. Okay, so here we go. The derivative of the top would be 1/2 x to the -1/2 multiplied by the bottom, which is x squared plus 1, minus the top, which is x to the 1/2 multiplied by the derivative of the bottom, which is 2x over the bottom squared. I just want to check that my mind's on polynomials right now from the last class. Derivative of the top looks okay, would you agree? Multiplied by the bottom minus the top times the derivative of the bottom. I think we're good. Now, there's two things that we want to do here. One of the things you have to do eventually is to factor everything completely on the top to see what might potentially cancel with the bottom, and you factor everything on the top to remove negative exponents, and you factor for a lot of reasons. But the other thing we would like to do is eliminate fractions within fractions. And you could, I guess, factor 1/2 out of the top, but I think that's not really a smart, wise move. I think the first thing you want to do is multiply the entire top and the entire bottom by 2. Now, we're also going to, in the next step, factor. And some of you might be tempted to multiply everything by 2, top and bottom, and factor simultaneously. You have to weigh your risks with that, because I think if you do them both at the same time, you're likely to make a mistake. So I want to get rid of that half. I'm multiplying the entire top by 2, which gives me dy dx equals, well, 2 times, and I want to be clear here, this is an entire term. So when I multiply that term by 2, this half goes away and I'm just left with everything else. Okay? So I'm left with x to the -1/2 multiplied by x squared plus 1. And then I have minus, I'm going to have 4 x to the 3/2. And I will discuss with you right now what just happened there. I get a 4 because when I multiply this second term by the 2, this 2 and this 2 multiply to give 4. And then I have x to the 1 multiplied by x to the 1/2. So when I multiply a common base, I add the exponents. That's where the 3/2 is coming from, 1 plus 1/2. And this is, of course, over 2 multiplied by x squared plus 1 quantity squared. And now when I'm looking at these two terms, Enrico, this term minus this term, I can see there's a common factor of x to the -1/2. Well, I shouldn't say I can see there's a common factor of x to the -1/2. I don't really see it that way. I just say I have to factor out the lowest exponent. And the lowest exponent would in fact be x to the -1/2. So I will take that out, and I will have left x squared plus 1 out of the first factor. This set of brackets here is totally unnecessary. I'm just putting it there to indicate it's the leftovers of the first term. I'm going to have minus 4, and I'm going to have x raised to an exponent which, when added to the exponent I took out, takes me back to the exponent I started off with. So this exponent that I'm worried about here is some number that when I add it to -1/2, it takes me to positive 3/2. And sooner or later, you'll just get this on intuition. You'll go, oh, it's squared, right? It's 4/2. And this is over 2x squared plus 1 squared. And we're really close to being done. This x to the -1/2 exists as a factor in the numerator, and because of that, I can move it to the denominator as a factor and change it to a positive exponent. My denominator of the derivative will have a 2, an x to the 1/2, and an x squared plus 1 squared. And it's also going to have 1 minus 3x squared on the top. Oh, the 1 is here, right? Plus 1. But then I have x squared minus 4x squared, which gives you negative 3x squared. And again, we want derivatives or expressions in this course in general to be nice and tidy in terms of factors. Like on the top, we want to be able to see a factor. On the bottom, we want to be able to see factors. Many of you might make the argument that the top can be factored that way. The only advantage in doing that is to see that x equals plus or minus 1 over root 3. But I can see that here. If I set this equal to 0 and move the 3x squared over and divide by 3 and take the square root, I get the zeros of it. Anyway, are you good with that? Mm-hmm. Okay. Other questions?
2e.
2e?
Yeah.
All right. We're going to have to use the quotient rule here. The numerator is x squared plus 2x. The denominator is x to the 4 minus 1. The derivative of a quotient says we take the derivative of the top. So I'm going to scream through this first part showing all the pieces, and then we'll stop and we'll evaluate it, then we'll simplify it. But the derivative of the top is 2x plus 2 times the bottom minus the top, which is x squared plus 2x times the derivative of the bottom over the bottom squared. So would you be in agreement with those pieces that I got? That's not the problem, right? I mean, that's the start to the problem, but now we have to decide what to do with it. And this is a very, very peculiar case. Because normally I would say we want to factor everything first. But I don't really see a common factor when I look at it in this form. What I'm going to do here, Hayden, is this first term, I'm going to factor slightly. Okay. Now, how many of you realize you can factor x to the 4 minus 1 a lot? Okay. I didn't factor it to begin with, because if I factored this to begin with, so the bottom is a difference of squares that factors into x to the 2 plus 1, x to the 2 minus 1, and x to the 2 minus 1 further factors into this. Does anything cancel here? Okay, so if I were to now, say, differentiate from that form, and I go derivative of the top, since I factored it, I would have to use the product rule to find the derivative of the top. Do you catch my drift there? If factoring it, this was simplified. That was just a reminder for me. If factoring it leads to something simpler, then by all means you want to do that to begin with. You know, maybe we could factor it and the whole thing cancels and you're left with 5x. Well, the derivative's 5 then. So that's why I didn't factor it completely to begin with. The other thing I'm pointing out is I said I'm going to partially factor some of this stuff to get common factors out. I'm not going to factor the x to the 4 minus 1 here because I'm not going to see an x squared plus 1 or an x plus 1 or an x minus 1 anywhere else. So my idea here is to simply take the 2 out of this top and have x plus 1 and x to the 4 minus 1 minus, I'm going to write this 4 in front and write 4x to the 4 and have x plus 2 here. So I've moved the 4 close to the front and I factored an x out of this and put it on the x cubed. Are you okay with that? This isn't really this isn't really helping me much. What I'm doing is staving off the inevitable. And the inevitable, that means to put it off. The inevitable is to multiply all that stuff out on the top. But the less I have to multiply out on the top, the better. When I do all this, I discover something very disheartening or disappointing. The only thing I can factor out of the top is a 2. That's it. In other words, I might as well have just multiplied the whole thing out to begin with. But I'm going to take that 2 out, and I will have left, well, all this other stuff, I guess I should write it out. Are we okay with my factoring of the 2 out? So I don't know if I've explicitly mentioned this to you, but the reason why you now have to multiply it out, this would be a Math 20 idea with rational expressions, is you have to simplify this entire remainder of the top in the hopes that when it gets crunched together to something simpler, you can factor it and maybe one of those factors cancels with something on the bottom. And if it doesn't, it doesn't, but it needs to be factored anyway. So I'm going to clean this up now by expanding this out. I have to do a foiling here, x to the 5 minus x plus x to the 4 minus 1. Can you check my first, outer, inner, last, everybody, on that, please? And let me know if it looks okay. Noah, do you have a question? No? Okay. Does it look okay? All right. Then I have minus 2x to the 4. I'm really not liking the looks of this. No, 2x to the 5. Minus 4x to the 4. Are we okay with that? Yeah.
So if you were to plug in an x coordinate, you'd have to put it into the simplified version of the
No.
equation? You could put it into either?
Yeah. Yes. And I think this discussion comes about maybe because I was talking about simplifying earlier. If you wanted to, and we'll come back to this in a second, but if you wanted to determine the derivative, then your question is not an important one, right? But if you want to determine the slope, which is the value of the derivative at a point, you could go ahead and put a number in. Are we supposed to do that, or does it just say what's the derivative? Does question 2 just ask for the derivative?
I don't know.
It doesn't ask for the slope, does it? Okay. But if it does, then I would never, ever, if it said, what is the slope at x equals 1, I would never have even gotten this far. I would have stopped up here, right at this point, and I would have put that x coordinate in right there. Am I answering your question? Okay. So now we have to clean this up. What do I get? Well, I get negative x to the 5. Do you agree? I don't like that. And I don't just mean, I don't like it. I don't want a negative leading coefficient. I'm going to take a negative out. So when I add my x's to the 5s together, I get negative x to the 5, but I'm taking a negative out, I get x to the 5. My x to the 4s, I get negative 3x to the 4. Oh, yuck. And when I factor out that negative, I get 3x to the 4. And then I'm going to have, for my x's, negative x, but I factor a negative out, and I have negative 1, but I factor a negative 1 out. So I believe that this is where we are at. Okay? Now, I don't want to go further, because in Math 30-1, you learned how to factor these polynomials using the factor theorem. But I have a number of students in this class who are taking Math 30 with me right now, and we're going to do the factor theorem tomorrow. So I don't want to cause any confusion here. I don't know if this even factors.
I don't think it does.
Then I'm guessing this would be the answer in the back.
I think it's something like that.
Yeah. Okay. Other questions? Yeah.
Number 6.
Number 6? Okay. So at what points on this curve is the tangent line horizontal? If I have a curve, Amy, and it doesn't matter what the curve looks like, with this particular curve, there are going to be 2 places where the tangent is horizontal. Going to be here and here. Right? That's what a horizontal tangent means. What's interesting about a horizontal tangent is it's a maximum or a minimum. It's a very useful tool. But the bottom line is the slope is 0. A horizontal tangent has to have a slope of 0, and that means what this question is saying is the following. Where does dy dx equal 0? That's what the question is saying. So we need to find the derivative of this expression or this function and set it equal to 0. And this will be a perfect opportunity for me to explain to you the importance of having everything factored, top and bottom. dy dx, I'll just write out my thinking with the quotient rule first, and then we can discuss the pieces of it. I think that's correct. Derivative of the top times the bottom minus top times derivative of the bottom over bottom squared. Now, the fact that the derivative is a fraction, and if you want to find out where a fraction is equal to 0, the bottom line is it's where the top is equal to 0. If we wanted to find out where the derivative is undefined, then we would worry about the bottom being equal to 0. And in order for us to see where the top is equal to 0, you need to simplify the top. And at this level, everybody, simplify means factor. It doesn't mean multiply out. If you multiply this out, you are going to get a more complicated polynomial to solve than if you don't. I can factor out a 2x and be left with 2x plus 5 minus x. Are we in agreement on that? Again, I get going on autopilot and I don't necessarily overthink it, but I think that's right. And this is over. Well, who cares what it's over, right? We're interested in the top. So now I can see that the top becomes 2x and x plus 5 So where is this equal to 0? At x equals 0 and x equals -5. This is starting to mesh really nice with Math 30 right now, with our conversation for you Math 30 students that we had today. The zeros of this expression are the zeros of the top of the expression. And the zeros of the top of the expression are the numbers that make each factor 0. So what number makes 2x 0? 0. What number makes x plus 5 0? -5. So these are our two locations this way. I suppose since it said at what points means we want a y coordinate. So one of the points, I'll call it P1, is at 0, comma. I need to put 0 into the original expression. And coincidentally enough, I will get 0. Because I'll have 0 squared on the top. And I need to put -5 into the original expression. And I believe we'll get -5, I think, for a y coordinate. We will. So the second point, was my math right on that y coordinate?
The back says it's +5.
I think it's -5. I think it should be -5. We can, you know what we could do? Just do a low-level cheat here and sketch this thing. Was x squared divided by 2x plus 5? Yeah. Well, I mean, let me just go to our table, -5. It's -5 for sure. Okay, but I do want to show you the significance of this graph. So there is a point over here at -5 where the tangent is horizontal, and there is this point here at 0 where the tangent is horizontal. And by the way, we will, in Chapter 5, we will come up with much better graphs than your calculator ever could come up with. Okay. Have I answered your question? Okay, we're going to move on and look today at what's called the chain rule. And the chain rule is used at all levels in differentiation. Please, when I'm talking, can you not talk? Okay? It may be so quiet I can't hear you, but if you're talking, you're not paying attention. And if I see you're talking, it's distracting to me. The chain rule is something that you apply at all stages of differentiation. In fact, we've actually been using the chain rule in some of the differentiation we've done. It's just that the result is multiplying by 1 in everything we've done. And in more complicated situations, the chain rule is going to say we're going to have to multiply by something, and it's not going to be 1. So we're going to learn what the chain rule is, and we're going to use it to determine derivatives. So we're, as a warm-up, going to look at 3 functions. And I've got all kinds of function notation going on over here. I've got, this is like a blending of y equals and f of. On the one hand, I'm saying f of u is some variable, f of u equals u cubed. So if I said, what is f of 3, you'd say it's 3 cubed. If I said, what is f of r, you'd say it's r cubed. On the other hand, I'm saying y equals u cubed. It's the same thing, right? Traditionally, you would say f of x is the same as y. Well, because our variable is not x, it's u, I'm saying y is the same as f of u. So I can say y equals f of u, or f of u equals u cubed, or y equals u cubed. I have an entirely different function, though, which is u, and the u here is the u here. Okay? And it says that u is equal to a new function called g of x, which means to calculate u, you need to put an x coordinate in. You with me? To calculate y, you need to put a u coordinate in. Those of you who have completed Math 30-1 will recognize this is a composite function, where you take the output of one function and put it in as an input in another function. And then we have the third function, which is y equals f of g of x. Okay, but wait a minute. This is y in terms of u. This is u in terms of x. This is y in terms of x. These two are the same function. This is saying you take, to find y, you cube u. Well, u is g of x. This is saying to find y, you put g of x into f. Well, that means g of x is going to go in here wherever there's a u. So this is where the idea of a composite function comes in. Those of you taking 30-1 with me right now don't know what I mean when I say a composite function. But basically, if I go back to this f of u equals u cubed, and I said, what is f of hearts? You would say it's hearts cubed, right? Hope that makes sense. If I said, what is f of g of x, then it would be g of x cubed. And g of x is 2x minus 5, which is u. So it's u cubed. They're the same function. Okay? What's important here is this is y in terms of u, this is u in terms of x, and this is y in terms of x. And what that means, everybody, and there's no need to write this down, because it's going to appear that at many times through my explanation I'm going to be going in circles. It is possible when you have y in terms of u to talk about dy du. Don't write that down, because we're not doing that with this notation. It's possible here to talk about du dx. And it's possible here to talk about dy dx. There's three different derivatives there: dy du, du dx, and dy dx. It depends on the variable we're talking about. Okay, so now we're going to actually do some differentiation. If y equals u cubed, the question is, what is dy du? Well, if that u were an x, what would dy dx be? It would be 3x squared, right? The fact that it's a u just means we're using u for the variable. This is 3u cubed. What is du dx? Well, du dx is found by looking at differentiating that with respect to x. So this is like having a y. Do you have a question? Yeah. Thank you very much, Spencer. It should be 3u squared. Absolutely. I probably said cubed. But it's 3u squared, definitely. Ben, what would the derivative of u with respect to x be? It'd be 2. So you're hopefully getting kind of a handle on how to differentiate other variables than y with respect to other variables, right? Now the question becomes, what is dy dx? Well, just a second here. Dy dx is going to be the derivative of this, but g of x, this goes around in circles a lot, but g of x is f of u. Right? G of x is u, so f of g of x is f of u. And u is 2x minus 5. And f of u would be 2x minus 5 cubed. So what we are asked to find is the derivative of this function. And now we're almost back to something that is more comfortable to us, y's and x's. So how do we do that? Well, unfortunately, we have to take a pretty big detour, because the only way that you know how to differentiate 2x minus 5 cubed is to go 2x minus 5 times 2x minus 5 times 2x minus 5. And that's what we're going to do. We're not going to use the product rule. We're going to multiply that whole beast out. So y will be equal to this, And if I FOIL out the first two, I get 4x squared minus 20x plus 25. It's been a very long day, it seems like, for me. Can you double check my foiling out of the 2x minus 5 times 2x minus 5? I think we're okay there. Good. And by the way, I know there are a couple of you that would have just used the binomial theorem to expand this whole thing out without foiling. Now I'm going to multiply out 4x squared times 2x, 4x squared times negative 5, which means I'm done with the 4x squareds. I'm going to take the negative 20x times 2x, which gives negative 40x squared. The negative 20x times negative 5, which gives 100x. And now I'm done with the negative 20x. I want to double check just before I move on. That's 8x cubed, negative 20x squared, negative 40x squared, 100x. Now I'm moving on to the 25 times 2x, which is 50x. And the 25 times negative 5 is negative 125. How did I do for my arithmetic? Okay. So I add all of these together, and y is equal to 8x cubed minus 60x squared plus 150x minus 125. 8, negative 60, 150, negative 125. Enrico.
Shouldn't the 100 be negative 100?
Let's see. The 100 came from the product, I believe, of this and this, and they are both negative. But it's worthwhile to double check. I mean, at this level, everybody's going to make mistakes from time to time. The more you do, the fewer mistakes you'll do overall. But I've been teaching this for a long time, and I still make mistakes from time to time, right? So this is why, in terms of x, this is what we need to differentiate to find dy dx. We need to differentiate this. So dy dx will be 24x squared minus 120x plus 150. 24x squared negative 120x plus 150. Looks good. We should probably factor that, which is the standard kind of protocol here. Dy dx equals, I can take a 6 out. Can I take a 12 out? Does 12 go into 150? It doesn't, eh? So just 6 then, I guess. Take out a 6 and have 8x squared minus 20x plus 25. Six times 25 is 150. 6 times 20 is 120. 6 times 4 is 24. So it's 4x squared minus 20x plus 25. Is 4x squared minus 20x plus 25 factorable? I think it is. I think it's 2x minus 5, 2x minus 5. Isn't that what we got when we multiplied 2x minus 5 times 2x minus 5 earlier? I think so. Which means our derivative, dy dx, is equal to 6 multiplied by 2x minus 5 squared. Okay, so far So what? Well, it's going to come together here very shortly. Any questions on getting dy dx? Okay. So I want to talk about rates of change here in terms of multiplying derivatives. If we look at dy du, and let's just say that y is Yvonne and u is Uberto, people. And I'll get to why I'm using people in a second, okay? And du dx, u is Umberto and x is Xavier, okay? So what dy du is a comparison of something about Yvonne to that same thing about Uberto. And du dx is a comparison of Uberto's property to Xavier's, and then dy dx would be a comparison of Yvonne's to Xavier's. So let's say that dy du is 5. What does this mean? Well, let's just say that that means that Yvonne is running 5 times faster than Uberto, because that's what a rate of change means. It's how quickly y is changing with respect to x. So if dy du in this case is 5, y is changing 5 times more rapidly than u is. You with me? And we can talk about running or not, but the bottom line is y is increasing 5 times more rapidly than u. And u is increasing 7, this is just a number I've made up, 7 times more rapidly than x. So on the one hand, y is 5 times faster than u, but u is 7 times faster than x. How many times faster than x is y? How many of you have a number in your head? What do you think it is, Spencer? 35. It is 35. If Spencer is running 5 times faster than me, and I'm running 7 times faster than Parker, ha ha ha, as if I could do that, then that means that Spencer must be running really, really fast compared to Parker. I mean, Spencer's already outpacing me by a factor of 5 to 1, and I'm outpacing Parker by a factor of 7 to 1. You're outpacing Parker by a factor of 5 times 7. The answer is 35. And this is the chain rule. Believe it or not, the chain rule says that dy dx equals dy du times du dx. Now, that's one way to put it. Okay? Don't worry about this bottom part yet. Okay? Don't worry about the bottom part yet. And I know that this is taught this way initially because people look at it and go, oh, well, of course that's true, right? You can't cancel those. They aren't factors. They're what are called differentials. So it may look like it's simple to understand, but it's kind of complicated. So let's do this notation here. This g of x is like the u. Okay? So if you want the derivative, and this gets really messy, if you want the derivative with respect to x of a function, but the function is not a function of x, it's a function of u, then you find the derivative of the function with respect to u, and then you multiply by the derivative of u with respect to x. These are saying the same thing. So let me give you, well, let's finish the warm-up, and hopefully it will become clear. Example 1 says, find dy dx here. So what I am going to do is write out that y equals 2x minus 5 cubed. Okay? And I'm going to use the chain rule. And I'm going to be drawing some stuff on here and then erasing it. And I'm also going to tell you right now, There are many people that get through calculus without understanding the chain rule. They know how to use it, but they don't get it. And that may be most of you. I don't know. Okay? But if I told you that this function was actually this, okay? And I said find dy d this. All that means is you differentiate this with respect to what's in brackets. You bring the 3 down in front, right? You drop 1 from the exponent, and the base remains the same. Are you with me that that's dy, d green rectangle? Okay, now, totally different point. And my goal every year is to get just one more person than last year to understand why the chain rule works the way it does. One more point. Do you agree that this is 2x minus 5? So if I said find d dx of this, I don't think there's anybody in the room here that doesn't know this is equal to 2, right? So this is our u. And dy du is 3u squared. This is our u. Du dx is 2. dy dx is the product of those two things. Dy dx is dy du, which is 3 times, let's not kid ourselves, this thing is actually 2x minus 5. This is dy du. It's the derivative of the whole expression with respect to 2x minus 5 times the derivative of this with respect to x is 2. 2 times 3 is 6. And now, remember when we did all that work, we got the derivative? Okay, the nice thing is, now I know from experience, not everybody in the room is going to look at that and go, oh yeah, that totally makes sense. It's a slippery thing to wrap your head around, but luckily for you, I can tell you that the chain rule is this. Whenever you differentiate by using a rule that you've learned previously, you apply that rule to a certain function. Specifically here, the rule we would use would be the power rule, right? You swing the 3 down. What is being powered? What's being powered is 2x minus 5. That's the thing, that's the function that's being powered. So we swing the 3 down, the base remains the same, and we drop 1 from the exponent. Here's the chain rule in its simplest form in this case. You then multiply by the derivative of what you wrap the exponent around. You multiply by the derivative of what's inside. Okay? That's the bottom line. So you end up with 6 times 2x minus 5 squared. Now the chain rule is applicable to a lot of other things, as we'll see, but for the time being, what really happens here is we combine things now. You remember when we said if you had a number times x to an exponent, you move that exponent in front and drop 1 from the exponent? Remember that? So now we're saying if you have a number times something that's not x raised to an exponent, you bring that exponent down, the base remains the same, you raise it to 1 less, and then you multiply by the derivative of what the base is. It's the derivative of what's inside. So, for example, What's the derivative with respect to x of this? Think about this for a second. If you wanted to differentiate this prior to today, you have to take that trinomial times that trinomial times that trinomial and either expand the whole mess out or use the product rule within the product rule. We don't do that. I'm going to take, as I do this, one or two more cracks at really trying to make you understand what we're doing. The first step is to wrap the 3 around the 3x squared minus 4x plus 1. This 3x squared minus 4x plus 1 is your u. Okay? And what this is du, dy, du. It's the derivative of the entire expression with respect to u, 3u squared, multiplied by the derivative of what's inside, which is 6x minus 4. This, since what was inside was u, is du dx. And the chain rule says dy dx equals dy du times du dx. Bottom line is we're done. I'm going to factor a 2 out of this, and the 2 can hold hands with the 3, and we can write 6 out front, and we're done. That's it. In fact, the chain rule has made our lives very easy. Dy dx equals 6, then an x minus 2, and then a 3x squared minus 4x plus 1. Quantity squared. This isn't right. (3x minus 2). Correct? When I take the 2 out? So I took a 2 out of this. I put the 2 with the 3 to get a factor of 6. When I take 2 out of this, I get 3x minus 2. And this is what I mean. I'm going to start not talking about the chain rule as if it's some complicated set of procedures, and I'm just going to say, multiply by the derivative of what's inside. And every one of you will be successful in using it. Not everybody understands why it works. And you could get a degree in math and not understand why the chain rule really works. Okay, you could. I did. Well, no, I kind of got it. I got it figured out after I got my degree. Let's take a look at this one. I got it figured out when I had to teach it. Then I really had to figure it out. Do you remember yesterday when I said we had something that was like this? And I said you could potentially move that stuff on the bottom to the top with negative exponents. But I also said, but you don't know how to differentiate that. That would involve the chain rule. But then I also said, see if you can remember this. I said, there are going to be some of you that are going to be tempted, instead of using the quotient rule, to move stuff up top and use the product rule. Remember that? And I said, that is a bad thing to do, but I said there is one exception, and this is it. The exception is if the top is a constant. If the top is a constant, then it's a lot easier to differentiate this than it is to use the quotient rule. Because all I have to do now is wrap that exponent around that base, drop 1 from the exponent, and multiply by the derivative of what's inside, and I'm done. It's amazing how quickly you can get derivatives once you know the chain rule. So dy dx equals -2. I'll decode all of this for you in a second. Multiplied by 16 minus x squared to the -3/2 multiplied by -2x. So what did I do here? Well, I took this -1/2 and I moved it in front. -1/2 times 4 is -2. Whenever I wrap an exponent around a base using the power rule, which is what that is, the base remains the same. There are going to be some of you that will be tempted to put a negative 2x in here to differentiate the base and put it in there. You don't. The base remains the same. I drop 1 from the exponent, and where did the negative 2x come from? Caden?
Derivative of the base?
The derivative of the base, the derivative of what's inside, the derivative of what we wrapped the exponent around, the derivative of u, because that's u. And now we can put the 2x and the x together and get 4x by multiplying. Negative times negative is a positive over 16 minus x squared to the 3/2. And you're done. And I'm telling you, it would have taken you a long time to differentiate this problem without the chain rule. Assuming you could even do it. Yes, Hayden?
Why isn't the 4x negative?
Because we had a negative 2 out front,
Yeah.
and this is negative as well, so when we multiply them, we get a positive. Okay, 4x minus 3 raised to the 6, x plus 2 raised to the 6. Tell you what my plan is right now in my head. I'm just going to go a little bit more. I don't quite know how much further. Your assignment, which is due tomorrow, I'm going to take in Thursday. And we're going to spend the rest of today working on this stuff together and all day tomorrow doing chain rule stuff. Okay? We might move on a little bit tomorrow, but I don't want to finish this lesson with 10 minutes left and have you get very little practice. Okay? So I'm going to use the quotient rule. And the thing I would like to point out to you, not everybody gets this analogy at first, but it will grow on you, is when you look at 4x minus 3 to the 6 over x plus 2 to the 6. Now I admit I'm cheating a bit in my analogy by making this really big. But when you're very far away, let's say you're so far away that you can't see what that is, and you get closer and closer and closer, the first thing you should notice is that it's something divided by something. You may not even be able to read the details of it, but it's a quotient. So we're using the quotient rule. Okay? If this thing were that, then as you got closer, you would discover that primarily it's a power. So you would use the power rule. Yeah.
That is what we have.
Yeah.
What's the second one?
Yeah. Did I put a 2 down here earlier somewhere? Yeah. Okay, I meant to be a 6. So there's 2 ways we could do this. I could look at it this way. And I could say, oh, I'm going to use the quotient rule. Or I could look at it this way and say, I'm going to use the power rule. And I would like to do both with you. We're not in a race here to finish anything today. I would like to do both with you. I'll tell you from experience that I believe it will be simpler and quicker to look at it this way. I believe it will be. So the derivative of the top will be the following. So answer this question for me. Is what I've written the derivative of the top? It's not. The derivative of the top is found by wrapping the 6 around the base, which remains the same, dropping 1 from the exponent, then multiplying by the derivative of what's inside. The chain rule has to be used here. There's that factor of 4. Times the bottom minus the top times the derivative of the bottom. Is this the derivative of the bottom? Yeah, it is. We have to multiply by the derivative of what's inside, but what's inside is x plus 2, so you have to multiply by 1. This is a case of us using the chain rule, even though you're not aware you're using it. You do multiply by 1. And then we divide by x plus 2 to the 12 because we have to square the denominator. So everybody double check all of our work. But I think we're okay. So now we're looking at the top, which has two lowly factors. And they're complicated, but it has this factor minus this factor, and we are going to factor as much as we can. There's a 6 in each, isn't there? You can take a 6 out. There are 4x minus 3's galore. There's 5 here. There's 6 here. I can take out 5. What else do we got? There's a bunch of x plus 2's. I think we can take out 5, can't we? There's 6 in one and 5 in the other. What do we have left? We took the 6 out. We took out 4x minus 3 to the 5. We have a 4 left. And we have an x plus 2 left. Minus, we have a 4x minus 3 left. We're done. Well, we're not done. We have to write the answer now. But I'll pause there. Any questions with that line? And this, again, is unlike any math or science class. You should be looking at that and looking at each piece and doing the math to make sure you get it. So this piece is the factor that I took out of the top. If I take this times that, I get 6 times 4, I get 4x minus 3 to the 5, and I get x plus 2 to the 6. If I multiply this thing that I factored out by the 4x minus 3, I get a 6. I get a 4x minus 3 to the 6 because I have to the 1 and to the 5. And I have an x plus 2 to the 5. So are we okay with the factored form there? Okay, remember, whatever you have left after factoring, you clean up. 4x minus 4x is nothing. 8 minus negative 3 is 11. So this is times 11. Well, I'm just going to put 66. And I've got a 4x minus 3 to the 5. And it's over x plus 2 to the 7. Just want to check something here. Yeah. Where did the power of 7 come from? Ben, where did the power of 7 come from? So I have raised to the 5 over raised to the 12, which is raised to the 7 on the bottom. We've got a bunch of canceling going on. So that's the derivative. Now, I did tell you I wanted to do it by putting the whole thing raised to the 6, which we can, and applying the power rule. So let me show you what that's going to look like. And just because I have a preference doesn't mean your preference has to be the same. We have y equals how is my memory on that? Is that sorry? 4x minus 3? I must be stuck on a previous question. Good now? Okay. So do you get the idea here that when you come from very far away, the first thing you notice is the power? Right? That's the power that you bump into. And that means I have to apply the power rule, which means I need to take that 6 and multiply by the base, which stays the same, raised to one less exponent, And then I need to multiply by the derivative of what's inside, of what I wrapped the exponent around. But I wrapped the exponent around a quotient. So when I write multiplied by the derivative of what's inside, it's the derivative of 4x minus 3 over x plus 2. It's a quotient, which means I'm going to use the quotient rule, which is the derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. And you know what? I take it back. I like this method quicker. I can see we're going to get the answer a lot quicker now that I think about it. One of the things I want to be careful of here is some people want this number to be 12 or 10 or something. It's 2 because this is the derivative of what's inside. We're only looking at that thing that's inside at this point. How many of you see you're going to get an x plus 2 to the 7 on the bottom? You have an x plus 2 to the 5, and you have an x plus 2 squared. We get a 4x minus 3 to the 5 on the top. Guess what this is going to give you? It's going to give you 11, which gives you the 66. So I take it back. Quicker this way. But you never really know what's going to happen. So I think there's one more example there, right? Your homework, I'll tell you what, your homework is to finish that example, and I changed my mind. Your homework is to finish that example and get that turned in assignment tomorrow to me at the beginning of class, okay? So your due date for that assignment is still tomorrow. The only homework you have is that finish that one example, example 5 or whatever it is, and get that hand-in assignment ready to be turned in. By the way, how many of you have completed it already? If you completed it already, that means question number 2, you use limits to find. Okay? You could use the chain rule now. Let me give you an example. Let me give you a very quick example of something that, I feel really bad in doing this because it's almost identical to the question, right? If I said to you, what is dy dx? That's the derivative. I wrapped the 2 around the base, which stayed the same. I dropped 1 from the exponent, and then I multiplied by the derivative of what's inside. Well, this is what's inside, right? The derivative is negative 1/10. So if I want to know the value of the slope of the tangent at x equals 3, then I'd put 3 in here. With the chain rule, you should be able to do example or question 2 in about 5 minutes, really. Sorry, Caden. The one person who used limits.
I didn't think I would have time tonight, so I did it yesterday.
Okay. Was it a lot of, yeah. So,
Not that much.
do you mind?
Yeah, I don't.
This is Caden's work using limits, right? And it's a lot of work. It is a lot of work because it's a difficult limit to evaluate.
I remember doing an example like it before, so it was
Yeah. This would be the work here. You'd put the number in and get an answer. Okay, so do that one example. Get your assignment ready to be rolled in to me tomorrow. And